around the outside, and Emma's is like light gray. So like there's still one exposure.
Okay, I would like to have your attention, please. Thank you. So I know it's been a little while, but last week we talked about electrical potential energy. And I gave you a couple of examples. I showed you an electric field. Let's say that this is a charged plate, and the plate has a bunch of positive charges on it. And I place a positive, let's just say, proton in that electric field. Okay? And we said, as I go from here to here, am I increasing or decreasing potential energy? Decreasing. Okay? And the opposite would be true, would be increasing. Okay, let's say I've got a negative charge here and I go to this point here. Am I increasing or decreasing? Decreasing. Isn't that where it wants to go?
Yeah.
Okay, so that would be actually taking the potential energy and converting it into what? Kinetic. Okay, so if I were to then go the opposite, and I were to go this direction, I would have to do work to force it against the force of attraction, right? I'd be putting in work to give it what? Potential energy. Okay, then, right? I would have to apply work. This is not going to naturally go that way, is it?
Amen.
I would have to apply work to it to get it to go that direction, increasing the potential energy stored up in the field so that when I let it go, it will turn into what? Kinetic. Okay.
The potato. A hairy potato.
Don't think of it that way. It's not left is this always, right is this always. In this context,
No, I'm not saying always.
in this context, okay.
Increasing, decreasing.
As I go to the right, I'm increasing. As I'm going to the left, I decrease. In this context.
It's opposite charges, or it's the same charge.
That makes sense. I'm thinking in my head. I just never like to give always and everys.
Oh, I know.
Yeah.
Trust me, I know.
Well,
Because every time I ask.
because every time it's an always and every, there's always a exception, and then not always.
There was a 5% test with always and always. We always do this. I feel like that. I'll say that.
Right.
5%.
Okay, so this is going to lead us into a couple things. Oopsies. Electric potential. Okay, equals the work that must be performed against the electric forces to move a charge from a reference point to a point question. So when I take this charged particle and move it in that electric field, that's called electric potential. Now that's not a super important vocabulary word. The next one we're going to do is way more valuable. Okay? But just know that you're giving it electric potential or it's losing electric potential. It's basically increasing potential energy or decreasing electric potential energy. Okay? The next one is the one we're going to use the most. Did you guys do you want time to get that in your?
It's in our
Okay.
Oh, wait.
There should be two equations.
Wait, it's just velocity equals.
It's not velocity.
Oh, wait, yeah.
What does it mean?
That would be no.
Okay? Yeah, so do you have this one in there?
Yeah.
Yeah. So you have two,
Yeah.
or it's going to be three, I think. But
That's probably just an electric.
Alright, this is the one I'm going to talk the most about. So V is not what we usually have been accustomed to thinking V as. The V is known as potential difference, and its unit is a volt. You've probably heard that before. Okay, this is really the chapter where we talk about and we figure out the volts that are in this battery, or the current that is flowing through a wire based on this much voltage and this much resistance. Okay, that's really this chapter. Mathematically, it's significantly easier. Okay, then last chapter. As far as a conceptually, they're probably similar. Okay? So, I just said electric potential. This is potential difference. Based on just the sheer words, what do you think the difference is?
One's charged by the other.
Sorry, I had two people talking at once. I wasn't able to say it again. Joyce?
Your initial, or your final minus initial.
Kind of. All right, so when I say the potential difference, it's the difference in their potential energy from this location to this location. So if I move this object from here to here, there's a certain potential difference between those two locations. Now, usually when we talk potential difference, it would be the difference in potential energy from my starting point to my ending point. So yes, it a lot of times is just simply final minus initial, but it could technically be between any 2 points. Is there a potential energy difference between these 2 points? The difference in that would be your potential difference. And its unit is the volt, is a volt. Okay? And you can see this in the equation. Voltage is really the change in potential energy. Yeah. Wow, right. Can't do it.
I should probably just put the practical one in, shouldn't I? Visual concept?
I'm gonna make, I'm not gonna start.
Would you stop that?
Yeah, that's what.
Oh, no. Say goodbye. You can take another number. That's not.
If a positive charge is released from rest in a uniform electric field and moves a distance d, there is a change in the electrical potential energy of the charge because of its displacement. The reference point or 0 point for electrical potential energy must be chosen. Here the reference point is point A. If the charge returns to point A, its change in electrical potential energy is 0 because the displacement, delta D, is 0. Only the difference in potential energy is physically significant. The equation for the electric potential energy of a charge Q in a uniform electric field E shows the simple dependence of potential energy on Q, E, and delta D. Just as the gravitational potential energy of a mass falling through a gravitational field decreases, the electric potential energy of a positive charge moving in the direction of an electric field also decreases. Since potential difference is defined as potential energy per charge, the expression for potential difference in a uniform electric field is the potential energy divided by the charge. In this equation, displacement is taken to be in the direction of the electric field. Displacement in a direction perpendicular to the field.
That's making me dumber. Sorry, guys. That was really difficult to follow, wasn't it?
Oh, I tuned it out.
If you say so.
Her voice makes it
This
so.
doesn't even make any sense to me.
Her voice is so easy to just
I
tune
know,
out.
exactly.
It's almost like a computer.
It's like
Yeah,
the thing that
I was gonna
Fisher-
say, this doesn't make sense anyway, because she switched the P divided by Q as the change in V. That's not what this is.
Okay, don't.
Change in V is the
Don't
change
pretend
in
like you're
potential
feeling
energy.
sometimes and then not the other two.
Oh,
So, yeah, all right.
So I'm talking to Jesse.
I think just me saying this, so the only thing that I maybe was helpful about that is it did say that you have to set a reference point, which that's kind of important, but it's always going to be the difference between your two locations. Now, most of the time when we're talking about electricity in the context of like going through a wire, it would be how much potential difference there is between the wire at the beginning and getting back to the battery. Does that make sense? Okay, so normally we're not worried about choosing a location. It's usually just the beginning point and the ending point. Right? So here is the potential difference in a uniform electric field. Did I explain what a uniform electric field was?
Not really.
Okay, so this is a uniform electric field where the lines are parallel. Typically this is going to be like if you had two charged plates. Oh, if this was like a bunch of negative charged. And then the electric field lines would be straight parallel from one plate to the other. Okay, we actually will talk about a capacitor is a charged plate. Okay, you can charge a capacitor, move it, and then use it to do work.
Is it usually like that in real life, or is this just like kind of like making a time?
Well, yeah, this is simplifying some things. Absolutely. Okay. Now, if you were just talking about like, I mean, we did electric field lines last chapter, and they weren't parallel, were they? And especially not here. Okay. So, yeah, it's gonna make it a little bit simpler. So yeah, you can kind of say it's the same idea as a frictionless vacuum. Okay. So, you've seen this word before, huh?
Yeah, multiple times.
So if you have groups of charges, you just add the potential energy on that group of charge. Like adding vectors.
Oh, no.
Yeah.
My math is easier.
Yeah, we actually are doing this.
Praise God.
Okay? I think that's it.
What's the units for volts?
What's the unit for what?
Volts.
That is the unit.
It's a V.
Symbol? A volt is a unit.
So you would say
Potential difference is 13 volts.
So you just had to write out volts. There's no.
You could say change in V is 13V. I know that's kind of goofy.
that's
No, it's not.
This is the symbol
That's not that
for potential
You ever seen a battery before?
difference. And this is the unit for potential difference, the volt.
That's
Okay?
how you write a volt.
I mean, look, you could say the change in
I mean, if you want to go
Meters is 15
VOLTS,
meters, it's the same thing.
so it doesn't bother you, you can. Yes.
What does the volt identify, like in a battery? Like if you got a 9-volt battery or something?
It tells you how much charge you've built up. So basically, like potential difference would be how much potential energy there is from inside the battery to the other side of the battery where there's none.
So it's like how much
Replace the battery.
can be stored like in a car battery? There's
Well, you can
12 volts.
store, it's how much they chose to store. Yeah.
Change your lights on.
Pack it to make it.
So like, essentially, right, if you got a whole bunch of charges that have been forced into a battery, right? Then as soon as you connect that battery to a wire, those electrons are gonna start flowing from a high potential to a low potential. Does that make sense?
Yeah.
From a position where they have a lot of potential energy, because those electrons are really close to each other, through the wire to a region that has low potential energy.
Then will it become like an equilibrium almost?
I mean, eventually that's when the battery dies. Yeah. That's what we would call the death of a battery, would be equilibrium. Okay, let's do this problem.
I need to figure it out. Make this out.
And so, that, like, when you're talking about an electrical power plant, that's shooting out a bunch of, a bunch of electrons. So it never doesn't really run out. Well, I mean,
plants that are
yeah.
powered.
Yeah, not yet.
That's why we need nuclear power plants. Or
Amen.
Okay, here we go. A charge moves a distance of 2 centimeters in the direction of an electric field. Okay, so it looks like we got a D.
15.
seeds in the soil.
Let me finish reading the context of the problem so that I know. I don't know.
Oh, okay.
Usually yes, but the best way is to look at its units. Okay? We have an electric field. What do you think that is?
Big boys. Big
What variable? Oh, E. What did you say?
Big boys.
215 big boys.
Then he also says he's gonna drop 18 on your mom. I know, but it's a normal phrase.
I mean,
I
don't get my mind on basketball.
If you're talking about the context that Kramer's talking about, like, yeah, that's normal.
What is drop
I don't play
18?
basketball in my
It
basement.
means you score 18 points. That's like the most common.
See? I told
I don't watch basketball.
It's like the most common
Yeah, the
basketball.
people who play sports get it, the people who don't
It's like the
don't.
most common basketball.
It's not like I'm not around basketball enough.
Probably 25.
Like, I've never been at a game and have someone say,
Okay, normally you say, I dropped 18 in that game, not I dropped 18 on your mom in the basement.
Well, okay, if someone, listen, if you're guarding me and I drop 18 on you, I dropped 18 on Steven. How does that not make sense?
And you can say like,
You would describe the
If I dropped 18 on Steven in the driveway.
You describe the sexual encounter with a.
You just think sexually all the time.
Who does that with their mother?
Exactly, that's the joke! That's the whole joke! I don't get it!
Oh, Kramer. I love this
all these
sexual.
symbols. It's so
I just that. So we've got a charge moves has electrical potential energy decrease of 6.9 times 10 to the negative 19. That's going to be.
That's V.
We could say that. Yeah, that wouldn't be a good way to say it. We could say change in V slash change in potential energy because they're the same.
Yeah.
So that's anything.
They're the same.
Yeah, it's just.
Potential difference is a change in the potential energy. It's what it is. It's the difference in.
So why are there two different units for it?
Yeah, it's energy.
Wait, but there's two
We even call
different.
that volts player.
It's
If
volts.
they're the same
doesn't
shape.
Yeah, I want to find something investigate.
So I'm
My
trying.
life.
I know,
So
but
I'm gonna
how
show
are
you
they two
myself.
different?
To find Q that high.
Yeah.
So I hate saying technically this
I think
is per
sorry, son.
cube. So they're different in that
It just.
this is the difference per charge. So so when I say they're the same, they're basically the same, but it's just per charge versus not.
Like the first.
So you can think of them as the same. Okay.
what is 6.9 times 10 to the 19? Is that Q?
No, it's changing V.
It says electric potential energy decreases.
Yeah, I thought, yeah, changing V.
And where is
I know, that's why it's not really that.
Yeah. I was kidding.
But they're so closely related.
Yeah.
Oh, there's also change.
Guys, change in potential energy and the change in volts are very closely related. The potential difference is the change in the potential energy per charge.
Oh, so it's gonna be a really small number.
Is that because the charge doesn't change?
Yeah.
To be fair, I thought we were using V equals change in PE.
Now we're getting rid of
So
Nah, you were wrong. We're using V.
I was just trying to show you that they're pretty much the same. They're very closely related. I mean, if you read the problem, it makes it very clear what it is. What is it?
Potential.
Electrical potential energy. Then it says it decreases. Okay, so that's going to give us a change. We don't know Q. We also don't know we don't know the change of potential energy per charge.
And not like a few question marks, but.
Yes, I did, Cheyenne.
I'm so confused. Why did you delete it and then or erase it and then put it back?
I'm just saying they're not the same.
You said they are the same.
They're very close to the same. No, they're not the same.
He's using two different equations.
I was just trying to say, I was trying to explain change in V and explain it based on change in potential energy. That's why I put them there. I'm sorry that putting them there made you very confused. That was not the goal. The goal was not to equate them as equal, but to show that they're very similar. Okay? Which one do you want to solve for first? Well, you probably need to solve for Q first. No, we don't. Solve for either first. Solve for Q. what equation do you think we're going to use to solve Q?
The one with.
Let's do it. And then you have to divide it by the.
Negative Q E D.
Yeah. So then you divide PE by ED.
Negative E.
That's not E.
Negative.
Negative ed.
Negative ed.
That's correct.
And then heading. Negative ed.
Half divided by yeah.
That's why I'm saying PE divided by
Okay? Now, this does say, it does say what here?
decreases. So it's negative.
So you plop the negative in there, it becomes a positive.
But doesn't that make up for the equation anyway? Since it's negative QE?
That's the why it's negative.
Oh, okay, yeah.
It's so that the sign work out.
Do we have?
Oh, we do need to change this to meters.
So we just point 0 to 0.
Is there a reason we need to change that?
Because Newton has a meter in it. Also, a joule is a Newton times a meter. So a joule is a Newton times a meter, so that's on top. And we got a Newton per coulomb times the meter. Look what cancels.
There's Newton.
These cancel, and then you have 1 divided by 1 over C, which is just what? C. So your charge, 1.6 times 10 to the negative 19. That should look really familiar. That's the charge of electron on a proton.
Will all our answers be that?
So the object that is being moved in this context is a what?
Electron.
Or a proton.
But protons don't work, so.
Protons can't.
Protons can't move.
Unless you're taking a test and there's.
Okay, now trying to find the change in V. We have a uniform electric field.
It could be a positive.
Every minute you waste is every minute longer.
There's a negative.
That's so profound.
So,
So, it's gonna be.
So you gotta go.
Everything you wait. This means it
Wait, so.
longer.
Oh, a minute longer. So you're
So,
at like
what was the,
15
like,
hours.
That's what
why do you have to do the first equation?
No, way longer, that was
It wanted to
7
find
minutes.
charge.
Oh, they find
24 hours.
guys, it says find the charge.
Yeah.
Okay, so it wants to find the charge, then it wants to find the potential difference between the two locations. Now, I know this is a little bit trickier, because what you have is a Newton times a meter per coulomb.
Isn't that that's a volt. That's a volt.
Okay, yes.
It's a
I
volt.
want to show you how it's a volt. Newton times a meter per coulomb. What's a Newton times a meter?
A
joule.
A joule divided by coulomb. A joule.
A joule per coulomb is a volt.
A joule per coulomb.
Our
You
final
might
test
want to
should
write this in.
Our final test should just be like, here's
But
this
that-
unit and derive it.
But that makes sense from our change in V equation earlier. We said
Let's go back a little.
change in V was the difference of your potential energy per what?
A joule.
What are the units for Q? Coulombs. What are the units for potential energy? Joule. So a joule per coulomb is a volt. So here's the difference between potential energy and potential difference. Potential energy is energy in joules. Potential difference is the change in the potential energy per charge.
In charge of school.
Okay? So what's the number there? I didn't.
It's negative 4.3.
So you could just say negative 4.3 volts.
I have a choice.
Is your potential difference? Yes.
So is there going to be different charges besides just like an electron? It's like if we already knew the charge of an electron, that kind of reference equation, you know what I'm saying?
Yeah, if we knew the charged particle was an electron,
Oh,
we
okay.
won't necessarily know that.
But so like, what would be an example of another charge?
Could be a group of electrons. Could be a positively charged sphere. Could be
So it's not just like.
And then the final charge.
Yeah, we can figure out the potential difference of
1.6.
a group of charges.
Yeah, okay.
So
Yep.
E is like,
Steven, that's just what he's saying, is do my body.
What?
Do my body.
they're on this.
Figure it out.
Potential energy difference between Isaiah and my body.
Any last questions here?
By the way, earlier when I had some units for a whole class, that's the graph units.
Oh.
So we call it a joule.
Okay, sorry, I misunderstood that.
Don't worry, I don't need.
Because your camera's off and then I'm gonna say this.
Don't worry, what?